Here's a number that will reframe how you think about web servers. Accessing the RAM on a computer takes on the order of nanoseconds, that's 10 to the power of -9 seconds. Accessing data on disk or over the network takes milliseconds, 10 to the power of -3 seconds. That's a difference of 1 million times. 1 million. And it's not just about latency. RAM has a transfer rate consistently in the order of gigabytes per second, while disk or network varies from megabytes per second to optimistically gigabytes per second under ideal conditions. This is what the book means when it says, I/O is slow. But wait, if I/O is a hardware problem, why does it matter for how we write software? Because most web applications spend most of their time waiting for I/O. They're not crunching numbers. They're waiting for a database query to return. Waiting for a file to be read. Waiting for an HTTP response from an upstream API. The CPU is sitting idle, staring at the wall. On top of this, there's the human factor. In many applications, the input comes from a real person, a mouse click, a form submission. The speed and frequency of human input can be many orders of magnitude slower than even the disk or network. So the central design question for a web server is not, how do I go faster? It's, how do I avoid wasting time waiting? That question is exactly what Node.js was built to answer. And the answer is found in two different I/O models, blocking and non-blocking. In traditional blocking I/O, the model used by most web frameworks before Node.js, when your code makes an I/O request, the thread stops. It literally waits. The function call blocks until the operation completes, which might take milliseconds or, in the case of a slow network request, even longer. The book shows a classic pseudocode example, data equals socket.read. That line blocks the thread until data arrives. Nothing else can happen on that thread in the meantime. Now imagine a web server built this way. When a request comes in that needs to read from a database, the thread handling that request is blocked until the database responds. While it's blocked, it can't handle any other incoming request. The traditional solution, use one thread per connection. 3 connections? 3 threads. 3,000 connections? 3,000 threads. But here's the problem, threads are not free. Each thread consumes memory and causes CPU context switches. Having thousands of threads sitting idle waiting for I/O means wasting enormous amounts of memory and CPU cycles. Non-blocking I/O offers a completely different model. Instead of blocking, the system call returns immediately. If the data isn't ready, it returns a predefined constant, essentially saying nothing to give you right now, check back later. The simplest non-blocking approach is to poll in a loop, keep calling read, until data arrives. The book calls this busy waiting. But busy waiting just wastes CPU spinning. It handles multiple resources on one thread but burns processor cycles for no reason. Neither model is perfect. The real answer is something better, event demultiplexing. Most modern operating systems provide a native mechanism that solves the busy waiting problem. It's called the synchronous event demultiplexer, also known as the event notification interface. The name demultiplexer comes from telecommunications. In that field, multiplexing means combining multiple signals into one so they can be transmitted over a single medium. Demultiplexing is the reverse, splitting a combined signal back into its original components. Applied to I/O, a synchronous event demultiplexer watches multiple resources at once and blocks, not spinning, but truly sleeping until at least one of them has data ready. When data becomes available on any watched resource, the demultiplexer wakes up and returns a set of events describing exactly which resources have data and what to do with them. The algorithm works in 3 steps. First, resources are added to a watch list, each paired with the type of operation to monitor. Second, the demultiplexer's watch call blocks synchronously, no CPU wasted, until any watched resource is ready. Third, for each event returned, the associated handler reads the ready resource, and since the resource is guaranteed ready, the read never blocks. After processing all events, the flow blocks again on the demultiplexer. Wait for events. Process them. Wait for more. This is called the event loop. With this pattern, a single thread can handle multiple I/O operations concurrently. Not in parallel, one thread is executing at a time, but concurrently, interleaved, without wasting CPU. And crucially, without the overhead of thousands of threads. This is the foundation of Node.js's efficiency. Now we can introduce the Reactor Pattern, the formal name for the architecture at the heart of Node.js. The Reactor Pattern is a specialization of the event demultiplexing algorithm. The key idea is simple: attach a handler to each I/O operation. In Node.js, that handler is a callback function. Here's how the pattern flows in 6 steps. Step 1. The application submits an I/O request to the event demultiplexer, along with a handler, a callback, to invoke when the operation completes. This submission is a non-blocking call. Control returns immediately to the application. Step 2. When the I/O operations complete, the event demultiplexer pushes corresponding events into the event queue. Step 3. The event loop iterates over items in the event queue. Step 4. For each event, the associated handler is invoked. Step 5. The handler, which is application code, runs to completion, then gives back control to the event loop. During execution, it can request new asynchronous operations, which adds new items to the event demultiplexer. Step 6. When the event queue is empty, the event loop blocks again on the event demultiplexer, waiting for new events. The pattern definition, as the book formally states it, handles I/O by blocking until new events are available from a set of observed resources, and then reacts by dispatching each event to an associated handler. That word reacts is where the name comes from. Notice something important: a Node.js application will exit when there are no more pending operations in the event demultiplexer and no more events in the event queue. There's nothing left to wait for. The reactor pattern and event demultiplexing sound elegant in theory. But here's a practical problem: every operating system has its own native interface for event demultiplexing. On Linux, it's called ephole. On macOS, it's Q. On Windows, it's the I/O completion port IOCP. Not only that, some I/O types behave very differently depending on the resource. In Unix, regular file system files don't support non-blocking operations at all. So to simulate non-blocking file I/O, a separate thread pool is needed outside the event loop. All these inconsistencies required a higher-level abstraction. That's exactly why the Node.js core team created a native C library called Libuv. Libuv's goal: make Node.js compatible with all major operating systems and normalize non-blocking behavior across all resource types. Libuv is the low-level I/O engine of Node.js and probably the most important component the platform is built on. Beyond abstracting system calls, Libuv also implements the Reactor Pattern itself, providing an API for creating event loops, managing the event queue, running asynchronous I/O operations, and queuing other types of tasks. So what exactly is Node.js made of? 4 components. First, Libuv, the I/O engine. Second, bindings that wrap and expose Libuv to JavaScript. Third, V8, Google's JavaScript engine originally developed for the Chrome browser, acclaimed for its speed and efficient memory management. Fourth, a core JavaScript library implementing the high-level Node.js API. That's the complete recipe. A minimal, focused stack that achieves remarkable concurrency with a single thread. And that single thread is why Node.js can scale the way it does.